Hello, Colton. Today we're doing something a little bit different, and 1-7 is the next section. But I'm going to give you this. You need to come get this from me. This is called the transformation handout. This is a grid that I use as kind of like a cheat sheet to remember the rules of like adding, subtracting to functions, how it moves it, all that good stuff. Okay. So I told them we're going to do a little quiz to see how you know these. Okay, or if you know these. So we're going to start here with a linear function. Okay. Linear, I'm going to put a little x and y axis, and a linear function, the most basic linear function is just y equals x, right? We know like y equals mx plus b, but if all the numbers like are at their base most, it's y equals x, okay? Linear function. I want you on that graph to show me-ish what a linear function looks like. Just sketch what a linear function is. I don't care which direction it's going, I don't care. Make him linear. Draw me a linear function. Okay? All right, then we're going to go on to a quadratic function. Quadratic is y equals x squared. All right? And I want you to graph on there what you think a quadratic function or an x squared function looks like. This is called the parent function, by the way. Parent function is just x squared. Okay? So, sketch, we'll go through here in a second. Sketch what you think he looks like, even if it's wrong. I don't care, even if it's wrong. All right, then the next up from quadratic is something called a cubic function. And that's y equals x to the third power. Let's see if you know what a cubic function looks like. Let's graph him. Okay, so do your best cubic function if you can remember. We're getting up high in there where you're like, I don't know if I remember quite what he looks like. Just make a guess. Okay? So you cheated, but you didn't realize you cheated. Hey, there you go. All right, let's do quartic. A quartic function, y equals x to the fourth power. Quartic. Y equals x to the fourth power. Try and see what you think he looks like. Should we go x to the fifth power also?
No.
No? Okay. You don't want to? Really? Are you sure? Yeah, we're gonna. I'm sorry, we're gonna. Quintic. Take a stab at it. Take a stab at quintic. We'll stop at quintic though, but then we'll do some others. Okay?
We weren't doing 5.
I'm sorry. Do you have some room to put one in front of linear or not?
No.
Otherwise, we'll put it back behind here.
No.
We'll do constant. You can go up the side. So constant would be like y equals 4. Graph what you think y equals 4 looks like. We've talked about that one already. Okay? Constant. Am I going too fast?
No.
Yes, a little bit. Okay. So linear, quadratic, cubic, quartic, quintic. Anything bigger than quintic is just a 6th degree and 7th degree and 8th degree, by the way. It doesn't have like a sextic or a septic or a octic or whatever, you know. It doesn't go that high. So 6th degree polynomial. Anything after that is just whatever degree. Okay? All right, let's do an absolute value. Y equals the absolute value of x. And graph what you think he looks like. We talked about him yesterday. Absolute value. Absolute value. These are pretty easy. You remember these? Okay? All right. The sooner you learn and can like put it in your brain toolbox of what these parent functions look like, the easier it will be on you. I promise. We talk about these all the time in the coming math classes and the rest of this year. Okay? So put these parent functions, the graphs of them, in your toolbox in your brain. Okay? All right, absolute value. Let's talk about couple more. Let's talk about square root.
I'm out of room after this one.
Can you go up the side?
Probably.
The square root of x. Let's talk about what he looks like. The square root, and then we'll do one more. We'll do the cubic root.
Whoa, I don't have
Okay.
room.
If you don't know, you can leave it blank, I guess, if you want to. We'll fill them in here. Cubic roots. The cubic root. Do you even know what a cubic root looks like? Like the root, the rational function, and then like a radical function, and with the 3 in there. cubic root, that means what do you take times itself 3 times to get that number inside, right? That's what he is asking for. All right, here we go. Shall we reveal the answers? Cubic roots.
Can we do the
Cubic roots.
whiteboards? This is hard.
Oh, we'll do whiteboards later sometime.
Does
You
Clay even
said
have
that,
Google
you said that we
Crossing?
would do them yesterday and we never did them.
What?
Does Clay even have Google Crossing? Did you get one possible?
What?
No, I've just been sending these videos to him over email. Yes. Good question. Okay. All right, let's reveal the answers. You know some of these. Linear. What's linear look like? A line. Like that. Okay. He looks like that. Quadratic looks like a parabola. He is a U. Okay. Do you know what cubic looks like?
Too little.
He looks like half of a parabola and the other half is going downward. It's like taking him like this and going whoop, right? Like
I
that.
thought it was just 2 humps.
Now, a cubic function, okay. Here you go. You ready for this? Yes, you're right. Yes. Just x to the third power doesn't have humps in him, but if he's like x to the third plus 3x squared plus 7x minus 1, that's when he's going to be like this. Does that make sense? So, this x to the third power is when he doesn't have like any stuff in the middle, right? The middle part, like the other terms after the x to the third power, makes him more of a hump. Okay? All right? Does that make sense?
Oh, I thought it humped on the
He does, but more.
Oh.
Like he has more humps in quintic. Okay. A quartic.
Everything wrong.
A quartic looks like a what?
Like a W.
Like a W. Okay? And technically that's a lie.
No.
I lied to you when I said that, okay? Because a quartic function just x to the fourth power. Are you listening? A quartic function just x to the fourth power looks like this. He's like a parabola but really flat in the middle. X to the fourth power plus 3x squared minus 7x plus 1. If he has other stuff behind him, that's when he starts to look W-ish.
Is it fine if we put these?
What?
Like
Yes.
W.
Yes.
I put an
Yes.
M instead.
I always say he looks like a W because that helps me. Okay? So it's the stuff that goes behind the first term that makes the humps higher or lower, right? Okay? So if it's just x to the fourth, he looks like a flat tire. But I always just say he looks like a W because that's the image. Because very rarely do you ever have x to the fourth power just by itself. It's all the stuff behind it. Okay, and that's going to make the humps, all right? So x to the fifth power.
It's just a flat x to 3.
He is going to be x to the third power, but with an extra hump. So he's going to look like this. Ish. Right?
I got that one
X to
right.
the fifth can have 4 humps. X to the third can have 2 humps, right? X to the fourth can have 3 humps. It's 1 hump less than what the degree is, right? So that's what a quintic function looks like. All right, constant. We talked about this before. If you're graphing like y equals 4, he goes up to 4 and draws a straight line across. He is constantly 4, right? A constant function. That's what he looks like, okay? All right, absolute value looks like a V. He looks like a V, a perfect V. He comes to like a point at the bottom, right? Okay, do you know what a square root function looks like?
I do.
You do, because you cheated.
Yeah.
Do you know?
Does it look like this?
Go up and then flatten out.
It starts like this and it goes up, and it doesn't go completely flat, but it kind of like gets to the point where it's not increasing as rapidly, right? So he kind of like flattens out like that. Now, he stops here. Are you guys all watching this, the square root function? There is not an arrow on this end. It starts at 0 and it goes on forever. Why does he stop there and not have an arrow?
Put a
Because
negative
there are
under the-
negatives.
Yeah, you cannot take a square root of a negative. When you're taking a square root, it's saying what do you take times itself to get that number, right? Can you take two numbers times themselves to get a negative number?
No.
No. So he doesn't go forever that way. All right. Now, a cubic root. Yes, sir.
Is it on the bottom?
What?
Like for the cubic root?
Does a
Is
cubic
it the
root go
top,
like
but
this?
it also
It's the
has-
top and
He
the
goes
bottom.
like this and like this. So he's a little bit flatter than a square root. A little bit flatter than a square root? No, actually he's less flat than a square root. Whatever. He goes that direction and he comes back negative because you can take the cubic root of a negative number. So he goes back the other direction. Now, just FYI, a cubic root looks like,
A lightning bolt.
no,
Uh,
sure, maybe in Brady's brain.
It looks like
Cubic root looks like a cubic function, but on its
Side.
side. That's not a coincidence. That's on purpose.
Oh yeah, I was thinking
Yeah?
of that too.
Now, technically, also, check this one out. A square root is actually x squared, which is a parabola on its side, but the problem is we don't put the other half of the parabola. Why not?
It's not a function.
It's not a function, right? It doesn't pass the vertical line test. If we do the other half of the parabola, this would be like plus and minus square root. So a positive square root and a negative square root.
Okay.
Not square root under a negative underneath, but positive square root, negative square root. So we don't ever do the bottom side because what?
If you flip the x's and y's,
Then it is technically that whole thing, the parabola on the side. Yep. So like if you write it as x equals y squared, then it is legit this guy.
Give us an example of
Okay.
where, how it would go underneath.
What?
How it would go underneath.
What do you mean?
Because if you do a positive, like 64 to
Yep.
cubic.
The cubic root of 64 is 4. So it'd be over at 64 and up to 4, right?
So you divide it by.
Okay, but what if it happens if you're doing this cubic root of negative 64?
You can.
Yeah, you can.
You said earlier you can't take
A square root. A cubic root is saying, what do you take times itself 3 times to get that number? Can you take negative 4 times negative 4 times negative 4 to get negative 64? Sure, so negative 64 would be down at negative 4. Yeah. You can't take it times itself twice to get a negative number, but you can 3 times. That'll be negative 4. Yeah, that's why he goes back the other direction. All right, so put all of those graphs kind of in your toolbox in your head so that you can remember what they look like, right? If you flip over to the other side, it has some of these. We did constant. We did linear. We did absolute value.
All of them.
Don't look at this one. That's greatest integer. We're not going to talk about him in Algebra 2. This is a quadratic. This is a cubic. We will eventually talk about reciprocal, which is 1 over x. We will eventually talk about him, but not yet. And this is a square root, and this is a cubic root. Okay? You did last year? Hey, so then you know what greatest integer looks like. Okay, we'll talk about him, but we don't usually graph him because he's not very important. What are you doing? Put him back. All right, here we go. Let's go to the back side. Let's go over here, and what I want to do is we're going to look at this column. We're going to fill this column out, and then we're going to fill these first 4 columns out, okay? So let's do that first. We get out. Not okay. All right, we're good. Oh, yeah. At 3:30. Okay, so we're going to be fine. All right, this first column is a linear function. This is like y equals x, which we just said looked like this guy, right? Okay, so we're going to fill this column out. Are you ready?
Yep.
Filling this column out. And we might fill this column out instead, or at the same time. So skip this middle one right here. And we're going to fill in x, and we're going to fill in x squared. Got it? Everybody know what we're doing? We're filling in the x column, and we're filling in the x squared column. So I'll show you what these look like. Got it? Beautiful. We're going to fill those in. You can skip the 2x plus 3 column for now. We're not.
Should
No.
we not have crossed it out?
What?
I crossed
That
the whole
one.
thing out.
The 2x plus 3? That's fine. Yeah, you can.
Okay.
Yeah. Unless your work needs to bleed over into the other one. I don't care. If you write real big. Okay? All right. Are you ready for this? Here we go. These are the rules. This is what we're going to do, okay? We're starting with y equals x. Shh, you got to be quiet. We're starting with y equals x, and I want to move him 6 units up. Do you see where it says that? If I move him 6 units up, he will look like y equals what? X plus 6. That's going to move him 6 units up. So that linear function, you don't need to graph it, but he's going to be up here at 1, 2, 3, 4, 5, 6, and he's going to look like this, right? Got it? Okay. All right, if I'm going down 5 units, he will look like y equals x minus 5. Okay. If he's going 9 units to the right, this is where we got backwards yesterday. Put a little star over here in these 2 boxes and say use the opposite sign. So if we're going to the right, you're thinking plus. It's not plus, it's actually minus. So if I'm going 9 units to the right, that will look like y equals x minus 9. And I'm gonna put it in parentheses, even though those parentheses are not technically doing anything. I'm gonna put them in parentheses because I'll show you with the x squared what's gonna happen. All right?
Wait,
Now.
square
real quick. Real quick. These two kind of look the same, right? There's no exponent outside of the x minus 9, so those parentheses aren't really doing anything. So it's almost as if when you take a linear function and you move it down, it's the same as moving him to the right. Let's see if that checks out. Okay, this one, I moved this function from here to here, and I moved him, what was it, 5 units up?
Yeah.
Moving him 6 units up. 6 units up was the same thing as moving him 6 units left, right? If I'm going 5 units, what did we say? 5 units down, 1, 2, 3, 4, 5 units down. Is that the same thing as moving him 5 units to the right?
Yeah.
For a linear function it is, right? Not for a parabola though, okay? So, if I'm moving him 4 units to the left, he looks like y equals what? X plus 4, that's what he looks like, okay? Now, again, this x plus 4 is the same thing as like the x plus 6 if they were the same number. It's just gonna move him up and to the left versus down and to the right because they mean the same thing for a linear function, okay? These are the rules, okay? Before we go on down below, let's talk about how that's different from a quadratic function. So, if we're moving him 6 units up, he will look like y equals x squared plus 6. Okay, got it? If we're moving him 5 units down, he is y equals x squared minus 5, right? It's just tacked on to the end. Those numbers are tacked on to the end, okay? Now, let's talk about how this is different for a quadratic function. If I'm moving him 9 units to the right, he will look like
X minus 9.
the whole thing squared. So the square will go outside of the x minus 9. Do you see how that's a little bit different? So that is not going to be the same as what moving him to the left or to down is, right? Down and right is not the same thing for a parabola, but it is for a linear function, right? Okay. What about the 4 units to the left?
Y equals X plus 4.
Parentheses x plus 4, that whole thing squared. You see how that works? Okay. So that's what we'll do to him, okay? Now, the benefit of knowing how to do this, are you ready? If I know what x squared looks like, and I know x squared is a parabola, and I put like a plus 4 inside of there, all I have to do is know that that moves him 4 units to the left, and I don't have to create a table and plug points in to graph the darn thing, right? That's the alternative, is I have to plug points in and graph it from there, and that's really a pain in the butt. I would rather just know, like, this is what happens to it and do a sketch and be done, right? Okay, versus plotting points, okay? All right, let's go down this one. If I'm vertically stretching it by a factor of 5, what does it mean to vertically stretch something? Vertically means up and down. We're putting in a taffy puller. Think of like Willy Wonka in the Chocolate Factory where she comes walking out and she's like, I don't know, like 15 feet tall and she's like really skinny, right? She has been vertically stretched. She's put in the taffy puller, all right? So when we do this, it's y, I know, put me in the taffy puller, right? This is y equals 5x. Y equals 5x. Okay? We are multiplying by 5. So take my height and I want to be twice as tall. That means we're multiplying me by 2, right? Multiply on the outside. Okay, if you're vertically compressing, that means you are doing this. He's going to look like y equals 1/3 x. You're still multiplying, okay?
Could you also put X above?
Yes, technically yes. Yes, that's a good thought, okay? All right, a horizontal stretch. All right, just like next to horizontal up above here, we put a little star. Did you see that up above?
Yeah.
When you have a horizontal translation or a horizontal stretch or compression, we're going to put another star here because something weird is going to happen. Okay, you use the reciprocal. Kind of like you use the opposite sign, you use the reciprocal. Reciprocal. You use the reciprocal. Okay, what's a reciprocal? The opposite. So if I'm stretching it horizontally by a factor of 2, I'm going to put in 1/2, or I'm like dividing by 2, right? So I'm going to put it as 1/2 x. I'm going to put it in parentheses so that you get used to seeing that for the quadratic function. Okay, so he'll be 1/2 x. If I'm horizontally compressing by a factor of 1/4, he will be y equals 4x. Okay, now let's compare these functions right here before we move on, okay? It looks kind of like this function and this function looks similar to each other, right? Like they're both using whole numbers on the outside. Do you see that? Because horizontally compressing means like you're getting skinnier, right? If you get skinnier, you get taller. Or if you get taller, you get skinnier, right? Like sometimes those will go together. Versus if I vertically compress, these guys right here, vertically compress is this one. If I take a peanut butter and jelly sandwich and put it on my hand and I vertically compress it, what's it gonna do? Horizontally expand, right? So sometimes those will look similar to each other in an equation, and it'll look like a horizontal expansion versus a vertical stretch. Same thing, right? Okay? All right. Thank you, sir. I like to throw things and set them down in random places. All right, so are we good to go on that? Let's go over and see what it looks like in a quadratic function. So y equals, if I'm taking it and vertically stretching by 5,
You're just multiplying it by 5.
multiplying it by 5, 5x squared, like that, right? Okay? If I am vertically compressing by 1/3, he is y equals 1/3 x squared, right? Okay, now if I am horizontally stretching by 2, he will be parentheses 1/2 x squared. Now, if we square that thing, that technically, actually, if you want to run over into the next column, is actually saying 1/4 x squared. You see that? If we square 1/2 and we square the x, it's 1/4 x squared, right? So, if this is confusing to you, don't listen. But if you can handle it, here you go. A horizontal stretch by a factor of 2 is the same thing as a vertical compression by 1/4. Does that make sense? Horizontal stretch by a factor of 2 is the same thing as a vertical compression by 1/4. Okay, so that's how that works. All right, let's go to this one. If you are doing a horizontal compression by 1/4, he is y equals 4 in parentheses x squared, which actually is like saying y equals 16 x squared if we get rid of the parentheses. So in that case, a horizontal compression by 1/4 is the same thing as a vertical stretch by 16. You got it? Okay? Good?
Yeah.
All right, now reflection over the x-axis and y-axis. These have to do with negatives. Are you ready? All right, here we go. Y equals negative x versus y equals in parentheses negative x. Those look exactly the same, right? The parentheses aren't doing anything for that function. Okay, so I'm gonna draw this. You guys don't need to. Okay, here is my linear function. If I have a linear function like this, and I reflect him across the x-axis, he's gonna go down and he's gonna become this green one. Do you see that? He's gonna come down and become the green one. Okay, versus, let's say I take that same function and I'm gonna reflect him across the y-axis. Guess what? He looks the same as reflecting him across the x-axis. Does that make sense? Because it's a linear function, so it doesn't matter whether you're doing it across the x or across the y, right? It doesn't matter, okay? For a quadratic function, let's say this is y equals negative x squared versus this one, y equals negative x squared. The negative is in parentheses, okay? If I fix this one, if I fix him, what happens to the negative when I square it? It stays the same. Okay, so you mean to tell me that if I reflect a parabola over the y-axis, here's my parabola. If I flip him across the y-axis, which means I take him and I do like this, does he stay the same? Yeah, that parabola is going to stay exactly the same when I flip him across the y-axis. That's why he does not change, right? He has y-axis symmetry, right? Okay? All right, those are my rules. Let's go through and let's fill these 4 columns in really fast, okay? Because this doesn't take too long. Are you ready? This is how you cheat. This is your cheat sheet. Are you ready? This is how you fill in your cheat sheet. If you are doing a vertical translation, up or down, are you adding or subtracting, or are you multiplying? We're adding and subtracting, so I'm going to check that there. If you're going up and down, that means you're adding and subtracting. Okay? Now, am I doing it inside of parentheses or on the outside of the function? Outside, it's just getting tacked onto the end. So if I'm doing a vertical translation up or down, I'm tacking it onto the end and I'm adding it or subtracting it, right? You got it? Okay, let's go to this next one. We are doing a horizontal left or right, okay? Am I adding and subtracting or multiplying? Add, subtract, but this time I'm doing it inside of parentheses. So you can see for the quadratic function, he's inside of those parentheses. Got it? All right, now vertical stretch or compression. Am I adding and subtracting or am I multiplying? I'm going to multiply on the outside of the function, right? He's just tacked onto the front.
What do you mean by outside the function?
Good question. So if I compare like here, right here, the 5 is on the outside of the square versus here, he's on the inside of the square. The 5, the number is being squared also. Does that make sense? Yeah. On there, the 5 is not underneath of the square. Okay? So he is being multiplied outside of the function, okay? When I'm doing a horizontal stretch or compression, here I am multiplying, but this time I'm doing it inside the parentheses, right? And if I have it to the second power, I'm squaring both of them, right? All right, the last one. Reflections. Are you adding, subtracting, or multiplying?
Multiplying by negative.
You're multiplying by a -1, right? Okay. For a reflection over the x-axis, are you multiplying that negative inside the function or outside the function? Outside. For the y-axis, he's underneath of the parentheses, so he's inside. Got it? Okay, so here's how you cheat. Are you ready? Let's say I have the function y equals the absolute value of x plus 2, let's say, right? Okay? First of all, his parent function is the absolute value of x. That's what we identify first. Okay? Then we have to say, what is the 2 doing? Right? So is the 2 adding, subtracting, or multiplying? We're add, subtract, right? We're under that. Add, subtract, and is it inside the function or outside the function? Inside. It's underneath, right? So I want to go to add, subtract, and inside. Which one is add, subtract, and inside? Right here. Add, subtract, inside. So it's either going to be a right or left. And this time it's going to be a left because that means plus. Do you see how we decoded that? Yeah. It's like a thing, okay? We will here in the coming days, we'll get to the point where we have like y equals, let's say I have x, we'll do 2x plus 3 squared minus 5. Woo!
That's a lot of numbers.
Okay, what's his parent function? Y equals x squared. Okay, how many things are being done to it?
Multiply.
I'm doing 3. This number, this number, this number. All right, now, when you have multiple things going on, you have to do them in a specific order. You want to know what order you go in? It's not left to right. Kind of PEMDAS. Yeah, kind of PEMDAS. Here's how I decide. This is the last thing I'm going to say, so here you go. If I were to plug a number in for x, would I multiply it by 2? Would I add the 3 or would I subtract the 5 first? You would add the 3. Okay, what's the 3 doing to it? Left 3. It's moving to the left 3. All right, then, would I multiply it by 2 or subtract the 5? I would take it times 2. What's the 2 doing? Vertical stretch by 2. Okay, then I subtract the 5. What's the minus 5 doing?
Translation
Down 5. That's what this parabola is doing. So I have a parabola that's moving to the left 3, so this way. It's being vertically stretched, so it's going to be tall and skinny. And then I'm moving it down 5, so it's over here, right? Like from where it was to begin with. Got it? This is all like learning shortcuts, okay? All right, lots of shortcuts. There's lots of shortcuts. This paper, you want to make sure you keep him and don't lose him. We'll use him tomorrow when we go through the notes. We'll go through all of this again. Are you guys overloaded? Was that a lot? Not too bad. It's all patterns, kind of, okay? All right, there we go.